Good afternoon, everybody. Hope you're having a great time at GraphConnect. My name is Michal Bachman. I'm a founder and CEO at GraphAware. So we're a Neo4j solution partner, and therefore our job and mission is to help organizations around the world build awesome applications on top of Neo4j. And when people ask me what the #1 use case is for Neo4j, I tend to answer it's recommendations. But up until now, I've had no data, no empirical evidence to back it up. So I've done a bit of number crunching on the flight to San Francisco and found out that of all the vast number of use cases that are possible with Neo and that we consult around with Neo4j, 33% of our customers use Neo4j for recommendations as the primary use case. And in terms of revenue from our consultancy revenue, it's actually 44% of all the consulting revenue is for recommendation related use cases. So that makes recommendations a really important use case for Neo4j. We've been doing this, so building recommendation engines, both for clients and open source, for 2 years now. And so I would like to share some of the learnings with you today. And I would like to also shed some light on what we think is the future of recommendations with Neo4j. So let me just start by briefly going over the apparent use cases for recommendations. So as you know and as you can imagine, you could tell people what news they should read, what books they should buy, what products they should buy, people they should date on the dating site. You might want to flip it around and recommend products to people to products. So if you're a marketer and you're marketing a product, you might want to find out who the people that we should sell this to are. And there's some less obvious use cases like clinical trial matching, law enforcement, because we know criminals form networks. So we might want to use a recommendation-like algorithm to tip who a criminal might be. We could use it for event planning and meeting planning, as we heard this morning from Scott from the World Economic Forum, career planning, and plenty of other use cases. So typically, recommendation engines, if you look on the internet or in literature, are split into two kinds. One kind is content-based recommendation engines. So these pieces of software compute things we should suggest based on the features or characteristics of the items that we're about to recommend. So for instance, if you have watched cowboy movies a lot, then we're going to recommend more cowboy movies. That's a property of that movie, a genre. The other type of recommendation engines are engines based on collaborative filtering. So this is relationships between users and the items that we're recommending. So for instance, we will be recommending to a user, we'll be recommending items that similar users preferred. The good news is that both features and relationships, of course, between the items and users can be naturally represented as a graph. So to show an example, see if you can spot both, right? It's relatively easy. So Bob here rated American Pie with the 5 rating. That's the collaborative filtering relationship. So that's a relationship between a user and an item. But then we've got American Pie off-genre comedy, which is a feature of the film, of the movie. So we've got both types easily representable in a graph. Now, why would we want to do this in the first place? Well, on a high level, traditionally, recommendations have been viewed as functions, as mathematical operations on similarity matrices and user rating vectors and so on. And these traditional approaches take a global view of your data set. They operate on the large data set and treat the computation of recommendations as an analytical operation or perhaps a machine learning problem. And these are typically run on batch processing frameworks and so on. And they're typically pre-computed for this reason. And the big disadvantage of pre-computed recommendations is that they are pre-computed. So earlier this year, I went with my partner Daniela to Vietnam for a trip, and she bought a backpack for that trip. And it was a pretty crap backpack. So she went on Amazon and rated it 1 star, not fit for purpose. The very next thing that happens when we check in to our hotel. She goes on Facebook to do a check-in, and then there we go, as a recommendation for the very same backpack. So they know she's bought it, she's rated it really badly, and still it's being recommended to her as an item to buy, right? So this is more funny than anything else, but you can imagine situations in which an out-of-date bad recommendation will be harmful, will make your users or buyers angry. There's a few more disadvantages with the traditional approaches. First of all, when you detect a bad recommendation, it's not easy to prevent it from happening in the future because it may not be immediately apparent why that recommendation was served. So remember, the system is a mathematical function, and to a business user, that's a black box. That's a pre-trained, pre-built black box. And even if we did know what to change to prevent that bad recommendation from happening again, we would have to retrain our model, we would have to recompute our recommendations, and this is going to take a while. A final disadvantage of the traditional approaches to recommendations that I would like to mention is typically the lack of wider context. So, we may want to serve different recommendations to the same user based on where they are, what time of day it is, what the weather's like outside, which device they're using to access that service, and so on and so forth. And this is hard to achieve with pre-computed recommendations. So I'd like to show you a different approach, the graph approach to recommendations. It's very different because it takes a local view of the problem. So it explores the immediate surroundings of the user and potentially their context in a graph of their preferences, their behaviors, their social contacts, and so on. So the recommendation problem is viewed as a query, as a real-time query, rather than a analytical background computation or batch computation. And it happens on the most up-to-date data. So take InfoJobs as an example. This is one of our clients based in Spain. It's the largest Spanish job search portal. And we help them develop Neo4j-based social features into what was a plain old boring job search site. So here's a screenshot from the website where on the right-hand side there are some suggestions for people I may know. This is these suggestions are produced by quite complex queries on top of Neo4j in real time. The entire graph at this organization has about 200 million nodes and 500 million. That's 500 million of relationships. And all these recommendations are computed in real time, sub-100 millisecond times. So for us, that's kind of a proof that real time is real when you use graphs. There are other advantages to the graph-based approach. And most of them, or all of them, the reason why they happen or why they exist, these advantages, is that the recommendation logic in its entirety can be expressed and easily understandable, can be expressed as traversals through the graph. So this is something you can write and you can explain to people. So the other advantages of the graph-based approach include flexibility. What I mean by that is I can easily change the query, because it's just a query, and the next time it runs, I can see new results or different results. It's transparent in the sense that I can clearly see what the query is doing, because I can look at the query. And it's contextual in the sense that I can easily and iteratively enrich my model and the queries to take into account other things, context, make the recommendation engine more sophisticated by taking weather into account and taking the mobile, what kind of device they logged in with, and so on and so forth. So just to give you an example of such a traversal, and you've seen queries like this before. I'm sure you've seen a few Cypher queries today. But this is a traversal that computes a trivial recommendation. So for a user with ID 1, we're finding all the movies they liked. We're then finding other users on the second line or third line, other users that liked the same movie. We're then finding other movies they liked. That's our potential recommendation. And then we're making sure that the user we're recommending to has not yet seen that movie, so has not yet liked or disliked that movie. So that's a very simple, understandable example of a traversals through the graph. And you could understand it in the first place, but you could modify it, you could enrich it, and you could run it in milliseconds in Neo4j, even on large graphs. The reality, of course, is that real-world requirements of recommendations engines are much more complex than this. So I'm going to try to dive into a real-world example and shed some light on this. whilst we're going through the example, I would like you to keep two things in mind. One, try to think whether you could build or express a traversal that would solve that problem and how easy that would be. And on the other side, think of trying to build a black box that will encompass all the complexities into one, some kind of big black box kind of recommendation engine. So the example, imagine you're building this people you may know feature on LinkedIn, for example. I think you all use LinkedIn, so we know what that feature is about. And I think this is a reasonably small room for me to do this. So let's say we're building this feature. How would we go about this? So especially front rows, come on, shout at me. How would you start looking at people you may know? What aspects of the user's data that you have could you use to recommend people one may know? Same group? Same industry? Same school, so they worked. So they went to the same school together, worked together in the same company, preferably at the same time, right? Same professions. Give me more. So we've got friend of a friend, right? So you got common connections, so then you can recommend. There's a potential that they know each other. Yeah, you could take if this is a professional social network, but yeah, you could take other preferences from social networks and so on. So there's quite a lot of things you can do, right? So we came up with these things, and hopefully we actually mentioned most of them. So contacts in common, people sign up with Facebook to on your site, perhaps, so you have their actual Facebook friends, so you can use that information, stuff that you take from their mobile phones when they install your application, if they're on Android, and all these other things we already mentioned. So there's actually a lot of different kind of traversals you can express to find these recommendations. But that's just the beginning, right? Because we need to actually think about even more stuff. It's even more complex than this. So in the example where we have friends or contacts in common, does the fact that we have more friends in common make the likelihood of us knowing each other higher? Perhaps yes, but we need to think about this. When we said we work for the same company, does the size of the company actually matter? Yes, it does, right? Because if I work for IBM and you work for IBM, chances of us knowing each other are quite slim compared to if you work for GraphAware and I work for GraphAware, chances are I know you because I'm the CEO. What about emails that don't represent a person? So we know that two people were talking to the same person, so we think, okay, they have something in common, but that person may have been support@neotechnology.com. So if you email this kind of email address, that doesn't make me in any way connected to you. And then we need to take care about people that are already connected and people that already have a pending invitation and people that explicitly rejected someone because they, don't want to connect to them. Either they don't know them or it's my old boss I really don't like, so I don't want to connect to them. Then we have some recommendations that people have seen. We know that because we serve them, but they repeatedly ignored them, and perhaps that means something for our recommendation engine as well. So, over the last months and years, we've learned that all these complexities can be split into 4 high-level pieces that we need to be concerned with when building a recommendation engine. So these are the pieces. We need to, in the first place, discover some potential recommendations. Then we need to score them somehow so that we can pick the top 10 or top 20 most relevant ones that we're going to serve to the user. Then we want to remove the irrelevant ones, and by that I mean the ones that should definitely not be served, like that backpack for Daniela or like that person that you've rejected that you don't want to connect to them. And finally, we need to be able to measure the quality of our recommendations so that we can improve that quality. So I'm going to dive into each one of those separately and talk about it in more detail. So the discovery is pretty straightforward, I think, because that's a traversal through the network, like all the other ones. But this one can be easily explained, right? If we're recommending movies for Bob, we may express a traversal that says, okay, find me what he liked, find me what genre that movie was, and then find me other movies of the same genre. So in this case, we would land on Love Actually. We can run another traversal saying, find me what he liked, find me other people that liked the same thing, and then what else they liked. Hey, Love Actually again. So we're discovering potential recommendations, some of them maybe multiple times through different paths. We can express these traversals, of course, in Cypher or in Java code or whatever you want to do. Secondly, we need to somehow score these recommendations, the results, because we'll end up with potentially a large set of potential recommendations. So one way of scoring these things is to score the actual paths. So as I'm traversing through that graph, I could choose, for example, to apply some mathematical function on the ratings the users have given to the movies. So that could give some weight to the path with which I discover a potential recommendation. I could also apply functions at the end when I have discovered recommendations through some means. I could somehow tweak it. So I'll give you an example. If we have 2 friends in common or 3 friends in common, that difference should probably be bigger in terms of how relevant that recommendation is than if we have 11 or 12 friends in common, right? So you could apply to the actual number of times you have found that person through a traversal some kind of Pareto function that makes more and more friends in common less and less relevant. So we could apply some transformations at the end. Finally, we have a concept, or we talk about the concept of boosting or penalizing the scores after we have discovered a recommendation. For this reason, let's say to Michael, we're about to recommend Daniela. Then we may say, do they live in the same city? If they do, we'll boost the score by 1 point. Why do we do it this way at the end when we already discovered it and not at discovery time? Because London has, anything between 8 and 16 million people, depending whether it's night or day. That would be, right in the beginning, an explosion of the search space. So we don't want to do that. Instead, we want to use other things to discover those recommendations. And then at the end, we're going to say, okay, do they have the same location? That's a very, very easy and cheap operation, right? It's just 2 hops. Equally, you could apply some penalties. For example, if this was a dating site, you could take the ages of the 2 people and say the more different they are, the more I'm going to decrease the recommendation score, because if the age is too different, maybe it's not good for my dating site. So that's how we score these things. Next, we need to make sure we remove stuff that's clearly irrelevant. And then there's 2 subtypes of this operation, of this logic. We talk about blacklists and filters. Blacklists are stuff I know up front I don't want to be serving as a recommendation. For example, if I'm recommending movies to Bob, I'm not going to be recommending American Pie because he's already seen it. That is something about Bob that I know up front. So I can build up a list, a blacklist of things I definitely don't want to recommend. And the second one, filter, means after I've discovered potential recommendations, there might be something that disqualifies that thing from being recommended that I can only check after I've discovered it. So for example, if Love Actually was R-rated or something and Bob was only 12, at that point I would filter it out. Or if an item is out of stock. Or if a user on my social networking site has a privacy setting that is set to the maximum level I don't want to be recommended to anyone. So that's when we would filter these recommendations out. Finally, we want to be measuring the quality of the recommendations. And this approach makes it relatively easy because we have all these different traversals that discover things, score them, and then filter them out or penalize them. We can log something like this. We can easily build a system that says, well, I've just served a recommendation with this ID. We can give them some UUIDs and say, this was the input, this was the output. And this is the breakdown of the scores showing us why we have served that recommendation. So the total score of the recommendation was 2.0, and we know why. And then we can, because we have a unique identifier of that recommendation, we can correlate the user's reaction. So either they have accepted the recommendation by buying your product or connecting to the person that you've recommended, or they have ignored it, or they've explicitly, in some instances, said, I'm not interested in seeing this. They actually rejected that recommendation. And you can then take these things that you've recorded, take a large volume of this, and run some statistical analysis on that and find out which components in your recommendation engine correlate positively with the positive outcome. That means buy your product. So an example of where this was useful is in InfoJobs, again, that professional networking site or job site in Spain. We actually found an inverse correlation between how people accept the recommendations and the Facebook friendship score that was produced. Then we realized, okay, people just don't want to connect on a professional networking site with their friends from Facebook, so we just completely removed that part of the traversal because it proved to be useless, in fact harmful for the quality of our recommendations. So the good news, I have more good news today, is that you can do this too. We have an open source skeleton for a recommendation engine that runs on top of Neo4j. It's these ideas that I've presented so far distilled into an open source kind of architecture framework. It was released in January 2015, so we've already had quite a lot of success with it and implemented some real world production ready recommendation engines. And I'll show you one slide with Java code. That's the only code you will see from me today, but I cannot just stop myself from showing you some code. So if you use this library, what you'll end up with, and it might be too small for some people in the back to see, this is the whole lot. This is a recommendation engine, hypothetical, called People You May Know. And it's very modular, as you can see, so you can almost, if somebody was to walk into this room right now and ask us, what is it you guys are doing here? We'd be like, hey, we're building a recommendation engine. It's called People You May Know, and it's suggesting people based on shared employment, contacts in common, mobile contacts, shared studies. It's then rewarding them if they live in the same city and rewarding them if they live in the same state. And it's penalizing the recommendations if the person has already seen it before. And then it's filtering out or blacklisting people that are already connected, invited or rejected. And then it's filtering out people that have the maximum privacy setting. That's it. Of course, there's some code or traversals hiding behind these components, but you can see it's quite easy to understand, and at the end, very easy to modify by kicking some components out or bringing some more components in. So this is a plugin to Neo4j that uses the GraphAware Framework. I've introduced the framework here at this stage in San Francisco last year this time, so there's a recording of that talk if you're interested in that. You can use Cypher or a JVM language, and you're inheriting this opinionated architecture of ours in exchange for fast performance, flexibility, and the plumbing that it handles for you. So that's recommendations. Problem solved. You can go and build your own, okay? Easy. So I'd like to shift gears a little and talk about what we think lies ahead of us. So we've been talking about serving recommendations to passive users, right? We imagine a guy logging on to our website, and then we're just pushing some stuff to them. They haven't indicated what they want to do. But what about these users that are active in the sense that they have indicated to us what they are looking for? Typically, on websites, this is done using a search box, right? So people start typing something, they're looking for something. That's an indication of what they're looking for. So given that we have a powerful personalization system, a recommendation engine, at our fingertips, wouldn't it be nice to utilize this for personalizing the search as well? Turns out people are already doing this, of course. So if you go on LinkedIn and start searching for someone, so I just did a search for Michael, immediately the results I get are not some random Michael from LinkedIn, because there's probably millions of them. It's Michael Heyer from Neo and Michaela Johansson from Neo, and so on. It's my first level connections. So it's a very personalized search. And it turns out that the vast majority of our clients who actually use the Neo4j for recommendation engines, they would like to personalize the searches in their system as well. So with pure Neo4j, we can achieve some parts. It has some indexing, so there's a Lucene index in Neo4j that you can leverage for this. And that indexing is getting better. So the Neo4j 2.3 that was announced this morning has some improved text matching in Cypher and so on. But there are better tools for finding documents or things based on text matches. So people will be familiar with things like Solr and Elasticsearch. And so Elasticsearch being, we think, very popular recently. So I'm going to spend some time talking about Elastic as well today. We're strong advocates of using the right tool for the job here. So we believe that we're going to start seeing increasingly larger number of organizations adopting a new approach with other tools. So before I introduce that approach, let's just briefly go over the requirements. When a user starts searching for something, like another user, we want the close ones, the ones in their network, to come on top. When a user starts searching for a product on the retail side, we want to have the products on top that they are most likely to buy, based on whatever recommendation logic we have. So you could view this problem or this use case as a recommendation engine with a constrained set of possible recommendations, that being constrained by the user search, or what they've typed into your search box. So if we look at this from a recommendation engine perspective, the only thing that's different here is how the recommendations get discovered. Everything else is the same. They're discovered now not by traversing Neo4j from a single source, but they're discovered by a search engine like Elasticsearch, giving us a set of possible matches, right? These search engines produce a score as well, which we then, it's the same kind of score, the same idea that we have for the scoring of our recommendations, right? So one more perspective at this. We have been serving recommendations by starting with a user and then discovering them, maybe scoring them as we go. So we do it differently now. When we have some people searching in Elasticsearch, we now have a few things. We have a few starting points. We have the user, and then we have some pre-served or predefined, pre-found potential recommendations. And all we need to do is then, instead of looking for them, we just need to find the path between the user and the potential recommendation and apply the same logic again, the scoring, the filtering, and the measuring of quality to personalize that search. So we call this approach graph-aided search. It's always been my dream to coin a term. To those of you guys who use REST, you know, if you search for REST, the first thing you will read on all the pages is REST is the term coined by Roy Fielding in his PhD thesis in 2000-something. His name is so famous because of this. So I expect someone today to go on Wikipedia, create a page about graph-aided search, and the first sentence will be coined by Michal Bachman at GraphConnect San Francisco. That will make me very happy. Okay, anyway, we have a term, new term. We need to have a definition so that you can put that on the Wikipedia page. So graph-aided search, we think, is the process of finding the most relevant results of a query by combining the score produced by a search engine with the score produced by a graph-based recommendation engine. So in looking at it from an software architecture perspective, we need to do a couple of things. We have an application that's writing some data to Neo4j, and then we somehow need to replicate this data to Elastic so it can be indexed. And preferably, we would like to do this asynchronously so that it doesn't slow down our transaction processing. The next thing we want to do, of course, is that when people search something for something on our website, typically that search query goes to Elasticsearch. But now we want Elastic, as part of its magic, to go and consult Neo4j, consult the recommendation engine, to boost the score that it came up with, wait for the results, and then return those back to the user. That way you would end up with a personalized search result. So in order to make this possible, we need a few technical components. So number one, we need something on the side of Neo4j that will be responsible for replicating data to Elasticsearch and responsible for the error handling and making sure if things go wrong that things can be re-indexed and so on. That's one component we need. The other component we need is some kind of a plug-in to Elasticsearch or a module here on this side that will be capable of contacting some component running on top of Neo to boost the scores of the search and then return those. And third, optionally, we need that machine on top of Neo that actually computes the recommendation, which may or may not be the open source recommendation engine that I've just introduced. So today I'd like to announce, more announcements today, that we've released just a few days ago, the first part, this component, a production-ready component plugin that can be just dropped into the plugins directory of Neo4j and will replicate data transparently to Elasticsearch. It's configurable. We released version 0 just to give people some time to test drive it before we release version 1, which is going to be in a few days. So that's good news. It's all on GitHub. It's all open source. You can go and download it and play with it. The other component that we're missing here, Elasticsearch to Neo4j, that's being actively worked on. We have some really good prototypes, alpha versions, and this is going to be ready before the end of this year. If you have any questions about this component, there's a smart-looking guy down here called Dr. Alessandro Negro, so you can just shoot questions at him for this part of the project. Both of the modules, in fact, the Neo4j module, of course, is part of a larger set of modules that we built called the GraphAware Framework. So there's the recommendation engine, time tree libraries, node rank, which is page rank, some tools for testing and things like this. This is a framework that is entirely open source GPL, very active, production ready. So for the people who subscribe to Neo4j licenses through GraphAware, we also officially support these things with SLAs. They're all on GitHub, our website, and Maven Central. Within a few days of new Neo4j releases, we always release a new version of the framework compatible with Neo4j. So that means today I have to do some work on releasing something compatible with 2.3. So try the framework if you can or if you're interested. We've had a lot of interest in Elasticsearch integration. So it's ready for prime time. It's ready to be tried and tested. Give us feedback. If you can contribute, please do. Get in touch for consultancy or support if you're stuck. And I thank you very much for your attention. And we have, I think, 8 minutes for questions. The lovely lady over there has a microphone. If you want to ask a question, please.
The quick question. On the professional sites like the LinkedIn, the majority recommendations are pretty accurate, pretty accurate. The sites like the Facebook, they do provide the recommendation, but they add some random pictures so that you can connect. So what is the rationale behind those the random experiments? Is it a A/B switching, or is it something like they want to try out the other connections, which is no connections you have? No way I can find out in the Facebook how they trying me to connect with those other folks, which I never met in them live.
Well, I don't know how Facebook implements their recommendation engine, but I would guess that your assumption that there's something they're testing maybe a bad assumption. I think it's just wrong recommendation, to be honest. But if they may have some. I mean, I just read this story when Mark Zuckerberg was having fun with their friends trying to do a bit of data science and predicting which couples will break up based on the interactions they have on Facebook, and they were quite accurate. So maybe it's some kind of fun data science stuff we don't understand. I would personally just blame it on they don't know who to recommend to you anymore, so they're just recommending some random people. You think they're the smartest guys? Yeah, sure they are, but it doesn't mean that every recommendation they serve will be relevant. I don't know the answer to that.
I have like 2 questions. On the slide that you showed where we had the personalized search, the application was writing to the Neo4j instance and which was replicating the data to the Elasticsearch. So would it scale up in a real-time environment where there are constant writes happening to the system? And what sort of data do we send? Do we send the text data also to the Neo4j? Because the text data is mostly belonging on the Elasticsearch, I assume.
Yeah, so the integration, right? We build it so that you can configure things. But the primary use case for now, and this will evolve, is the first version of the project, but the primary use case is the following. You have Neo4j as your primary OLTP data store where you store most of your data or all of your data. Let's talk about sort of articles and things like full text stuff later. But you would store everything primarily into Neo. That's your system of record. And then asynchronously behind the scenes, we replicate this to Elastic so that it's indexed there and it's searchable. You configure what kinds of nodes, and what properties from those nodes will be sent over to Elastic and which ones you're not interested in indexing, right? In terms of scalability, what we use is the bulk API of Elastic. So actually, if you have a high transactional throughput, we store these transactions in an in-memory queue, and very frequently, almost continuously, we take chunks, whatever's there right now, put it in a bulk, and send it to Elastic. So it's pretty fast. Yeah, there's no problem with that, because actually you just shift them out faster than you can accept them, because you take whatever you have at any point and just ship it to Elastic with a REST call, and next one. So it's probably worth, if you have that concern, to actually test it, right? It's easy, just generate some load and see how it behaves.
Hi. So I'm building a recommendation engine for an e-commerce site, and we're deciding whether we should include browse behavior, and then whether we should summarize the browse behavior. What would be your take on that? So for example, I'm browsing a variety of books, and then I may even go back to them and may even visit them several times during the week. Would you put all that data in a graph, or would you just summarize, like, yes, you've browsed this one and this one and this one?
I think it depends largely on the volumes you're looking at. So we typically tell people, if you up to a few thousand transactions per second, you're fine in Neo. If you have a really large volume, large throughput website, where let's say you would have to be writing 50,000 transactions per second on Neo, then it's not the right place to put it. So depends how many users you have and what the usage patterns are. I would say for something like a really high volume website or system, I would store these ticks, if you wish, or these actual like page access data in something else, perhaps Cassandra or whatever, and do a daily or hourly summary of what the people are interested in, and then write that to Neo4j. If your website only has, I don't know, 100,000 or a million users, and it's not accessed that frequently, then it's no problem actually storing the data in Neo4j, because you have a relationship. This person visited this page, then if they visit it again, you can choose to either say, okay, I already have that information, or you can choose to increment a property on that relationship and say, oh, they visited again, so we just have a counter on that relationship and increment it. And that counter then can serve as the strength of how much they like that website. So it depends on the data sizes, I would say.
So, yeah, question here. We work a bit on different kinds of recommenders. Is that okay, like this? Most of the systems that we come up with are highly probabilistic in their nature, whereas the graph queries that you do are pretty much deterministic, save for some maybe randomization in scoring. So how would you go about implementing things with sampling systems and sampling methods based on your architecture?
So what I've shown is a deterministic system. I admit that in some cases we do sampling as well. The reason being, if we're looking for people who worked at the same company at the same time as you, if it's a very large company, that might be 1 million other people, for example, right? Because there's going to be, if you work there for a long time, like 10 years, you worked for PricewaterhouseCoopers, whatever, then there's going to be hundreds of thousands of people that work there at the same time as you, which necessarily doesn't mean anything. So if you've chosen your model to be that, where you actually have a very, very dense node, PricewaterhouseCoopers, then in order to make sure that my recommendation engine is real time, I would sample the relationships as well with something. We typically use something called reservoir sampling, because you don't know how many relationships you have until you've seen them all. So use that algorithm to sample the top, not the top, but the 1,000, like a sample of 1,000, for example. That's one thing you can do. The other thing you can do is you can choose based on, so when you're building the recommendation engine, you can put the ones that are potentially going to be slower in the bottom of the chain, and you can check whether you have enough time. So you say, I want a recommendation in 100 milliseconds, no more than that. And then as you're computing, you can see in the last one, oh, I still have 20 milliseconds left, then I can do this, or I don't have any time left, and I'm just going to skip that one.
Yeah, so that's all about the computational performance. But in the end, quite likely, you also want to balance between exploring what you know of a person and exploiting actually, and exploring relationships that do not yet exist, but you want to figure that out, right?
So I mean, so for things you have discovered at least, right? The easiest possible thing to do would be to add like a random booster, just one component, one line of Java code that will randomly boost some people's scores with some probability. That's one thing to do. For discovering stuff that's totally disconnected, that would be hard, but actually you will rarely find graphs in the real world that have disconnected components. So you will discover.
Isn't the idea of recommendations in a graph to predict the missing links?
It is. What I'm saying is you're hardly going to find a graph in the real world where there's an island that's not connected to anything else. So what I'm saying is the random boosting that I just described would probably be sufficient, at least for the first pass, to let the users discover new stuff that isn't probably that closely connected and so on. If that answers it partly.
Yeah, sure. I think later we can talk about recommenders for a couple of hours.
Cool.
We need to wrap up. So if there's any more questions, you should just take them, after.
One more or no? No, one more.
Well, the last one.
The last one. Okay. Good question. The question is how do you start, basically? How do you know what the score should be in the beginning, in the first place? The answer is pragmatic. You basically just shoot some numbers. You ask your business people, you think it's more important that the guys have some people in common, or you think it's more important they live in the same location, or you think it's more important that they work for the same company. So you work something out. You just sketch it out, and you just basically guess, and then you put it into a system and expose it to the users, and then you measure how they react to this, and you can tweak this. You can do A/B testing, A, B, C, D, E, F, G testing you can do, because you can deploy different versions of the recommendation engine and just choose one. Then you're recording which recommendation engine served this recommendation, and you can see which one performs better, and then you can improve this. So the answer is actually just start somewhere. That's better than spending half a year figuring out the magic mathematical formula, and then actually finding out it doesn't work for your recommendation. So we just, we say, okay, the maximum score is going to be 10. How do we attribute the different components to the different traversals, and let it run? Okay, guys, thanks very much.